Hi guys, welcome back. So I'm continuing my note cards studying series today with the note cards that I used to prepare myself for the physics GRE a few years ago now. As with the other note cards videos I just want to clarify that these were just ones I made for my own personal use, and I can't vouch that they will be helpful or accurate or useful for anyone else, but a lot of people seem to enjoy these and ask me to share them, and so I'm happy to do so and to provide a little quiz session for you if that's helpful. Okay, so today we are doing quantum mechanics and atomic physics. So these are actually together in my note cards because the book I was using put them together, but on the test they're listed as separate sections to know, and they are 12% and 10% each respectively, and so together they're 22% of the test, so it's a pretty big portion. And for me, at least personally, this was like what I was most rusty on. So a lot of these note cards are just like me trying to remember like kind of basic things. But yeah, this is our kind of hefty section to get through today. And as before, there will be a link to a PDF below so you can print these out if you want and use them for yourself. And the upcoming April GRE physics GRE has been canceled, but they should be announcing dates for when they're going to have it again in the fall. So keep an eye out if you are looking to take the physics GRE this year. Okay, so we'll just go ahead and get started. This might be a long one. All right, the Stark effect says delta H equals E dot R, and n equals 2 is the first state to show a first order shift, where E is the charge and big E is the electric field. The Lamb shift correction is an order of alpha to the third smaller than Bohr energies, and it splits the 2s and 2p level with J equals 1/2. The spin-spin coupling correction is of order alpha squared, and mass of the electron over mass of the proton smaller than the Bohr energies. And the transition between states is at lambda equals 21 centimeters and energy equals 5 times 10 to the negative 6 electron volts. The Zeeman effect that says delta H equals E over 2m times L hat plus 2s hat dot B, where E over 2m is the gyromagnetic ratio. The fine structure correction is of order alpha squared smaller than Bohr energies. The energy levels depend on total J and breaks the degeneracy in L. The Hamiltonian for the hydrogen atom, this is H equals negative h bar squared over 2 mu var squared minus E squared over 4 pi epsilon naught times 1 over R. The spin orbit operator, this is L hat dot S hat, and it equals 1/2 times the quantity J squared minus L squared minus S squared. Spherical harmonics eigenvalues. So L hat of Z times Y ML equals M H bar Y ML. And L hat squared of Y ML equals L times L plus 1 times H bar squared times Y ML. Hamiltonian of the one-dimension quantum harmonic oscillator. This is H equals P hat squared over 2m plus 1/2 m omega squared x hat squared. Or H equals H bar omega times A positive A plus 1/2. The coefficient of the basis function, C sub n, equals the integral from negative infinity to infinity of f sub n of x star times the wave function of x and t dx. The wave velocity of a free particle, omega of k, equals h bar k squared over 2m. The expectation value of operator A in linear combination is equal to the sum over k of lambda sub k c sub k squared. Absolute value of c sub k squared. The orbital and azimuthal quantum numbers. So L must be greater than or equal to 0, and then M is equal to L of L minus 1, L minus 2, etc. The momentum operator in 3 dimensions, p hat, equals I h bar var. The momentum operator in 1 dimension is p hat equals negative I h bar partial derivative with respect to x. The Hamiltonian of a free particle, h equals negative h bar squared over 2m and the second derivative with respect to x. A free particle's wave function and energy, psi of x equals e to the plus or minus ikx, and e equals h bar k squared over 2m. The Bohr model. So this says that electrons move in classical circular orbits with quantized L, where L equals n times h bar, and n is a positive integer. Electrons do not radiate as they orbit, so they're stabilized, and the energy transitions between shells match the Rydberg formula. For finite dimensional vector space, Diract notation, so a bracket, which is a kind of left angle, and then your value, and then the straight is defined as the complex conjugate of the transpose of your item. And a cross is also equal to the complex conjugate of the transpose of the item. The time-dependent wave function, psi of x and t, is equal to the sum over n of c sub n e to the minus I e sub n t over h bar times psi of n of x, little psi of n of x. Seven properties of time-independent eigenfunctions. So these are little psi sub n of x. So psi sub n for different n are orthogonal. Psi is always continuous. The derivative of psi with respect to x is always continuous except at boundaries where the potential is equal to infinity. Psi can be taken as purely real with no loss of generality. And for stationary psi sub n, the expected value of the momentum is 0. Psi sub n at e sub n has n nodes. And if the v of x potential function is even, psi of x has definite parity, alternating n. And if the energy is greater than the minimum potential required for psi to be, the energy must be greater than the minimum potential in order for psi to be normalizable. Yeah, this section was obviously a hard one for me. I had to write down like everything. Angular momentum commutation relations. So the commutation of Lx hat and Ly hat is equal to I h bar Lz hat, etc. So for different combinations of x, y, and z, it's equal to the other one over here. Quantum operators of angular momentum. So L hat equals R hat cross P hat, and Lx hat equals Y hat PZ hat minus Z hat PY hat, and again, this kind of relation can be carried through for all the different permutations of x, y, and z. Degenerate perturbation theory says that you can diagonalize the perturbation in the subspace of degenerate states. The uncertainty bound tells you that the uncertainty in A squared times the uncertainty in B squared has to be greater than or equal to 1 over 2i times the expectation value of the commutation of A hat and B hat squared. The Stefan-Boltzmann law says that dPdA is proportional to T to the fourth, or flux is proportional to temperature to the fourth. The hydrogen atom unnormalized ground state, psi sub 1 of R, is proportional to E to the minus R over A. The selection rules for atomic transitions. So this requires you to assume that the electromagnetic wavelength is large compared to the atom, and in that case, there'll be no transitions unless delta M is equal to plus or minus 1 or 0, and delta L is equal to plus or minus 1. The commutators of products of operators. So the commutation of A times B and C is equal to A times the commutation of B and C plus the commutation of A and C times B. So this is just a rule for how that works. The Bohr radius, this is A, little a, and it equals 4 pi epsilon naught h bar squared over mu e squared. For perturbation first order energy shift, you have E sub n equals E sub n 0 plus lambda times psi n 0 h prime psi n 0 with the bracket notation here. The Schrödinger equation. This is I h bar partial derivative with respect to t of big psi of x and t is equal to h hat times big psi of x and t. The Hamiltonian operator, this is h hat. This equals p hat squared over 2m plus v hat of x. It also equals negative h bar squared over 2m times the second partial derivative with respect to x plus v hat of x, except if the external magnetic field, except if there is an external magnetic field or if the potential is also time dependent. The fine structure constant alpha is equal to e squared over 4 pi epsilon naught h bar c. And this works out to approximately 1 over 137 as a value. Total orbital angular momentum, L hat squared is equal to Lx hat squared plus Ly hat squared plus Lz hat squared. And L hat squared commutes with all of the L sub I hats, so x, y, and z. Spherical wave function normalization in 3 dimensions. So psi of r is equal to r of r times y of theta and phi. Then the integral from 0 to infinity of r of r squared times r squared dr is equal to 1. And the integral over 2 pi and pi for theta and phi respectively is equal to y squared sine theta d theta. Those are like different spherical components that you need to integrate over, basically, to normalize. Spin 1/2. So this is when s equals 1/2. And so then ms is equal to either positive or negative 1/2. And s hat squared is equal to 3/4 h bar squared. This is the operator, the spin operator. The Pauli matrices. So for x, y, and z, the spin operator equals h bar over 2 times sigma of x, y, and z, where sigma are these matrices. So sigma x is equal to 0, 1, 1, 0. Sigma y is equal to 0, negative I, 0. And sigma z is equal to 1, 0, 0, negative 1. The general Hamiltonian in 3 dimensions, h, is equal to negative h bar squared over 2m bar squared plus the potential as a function of r. Okay, this one's like almost backwards, but anyway. So little psi of x is equal to the square root of ma over h bar times e to the negative ma x over h bar squared, where e is equal to negative ma squared over 2h bar squared. So basically, what are these? These are the wave function and energy of a delta function. I think the idea with this one is that I wanted to be able to recognize the form and be like, oh, that's for a delta function. Not that I necessarily wanted to memorize what they were, but like I said, this was a long time ago I made these. Okay, a Hermitian conjugate. So this is a little cross, a operator hat cross. And so the definition for a Hermitian operator is that a hat cross equals a hat. And so for basically if you have a and b and you have a hat on the right side, and then if you move it to the left side, that's a hat cross. I'm sorry, this is hard to explain with words. It's pretty clear when you write it out in the math notation, but okay, the function space Dirac notation. So if you have a bracket with x on the left and f on the right, then that is f of x. And if you have a bracket with f on the right and left on g on the right, then that is the integral from negative infinity to infinity of the complex conjugate of f of x times g of x dx. Again, words are difficult here. That's just a mathematical notation. The eigenvectors of the spin operators for x and y for spin 1/2. So you have up and down, basically. And for x, the up is 1 over the square root of 2, and then the matrix is 1, 1. And for y, it's 1 over the square root of 2, 1i. And then for the down factor, or down eigenvectors, sorry, it's 1 over the square root of 2, 1 minus 1 for x, and 1 over the square root of 2, 1 negative I for y. Annihilation and creation operators. So A is the lowering and A plus is the raising, and the commutation of A and A plus is 1. The virial theorem says that the expectation value of t is equal to the expectation value of the potential is equal to E sub n over 2. This is not general to superpositions, but does for the harmonic oscillator. So I think that means it is for the harmonic oscillator. I'm sorry. Hopefully these will be more helpful if you can print them out and look at them than listening to me try and say these out loud. Okay, so here's some more that I was just trying to recognize the function and not memorize it. So here's the function. H equals negative h bar squared over 2m, second derivative with respect to x, minus a delta of x. And this is the Hamiltonian for a delta function. Oops. Show you the back. Okay, and here's another one. So here you have a wave function, so little psi sub n is equal to the square root of 2 over a times sine of n pi x over a, and the energy at n is equal to n squared pi squared h bar squared 2ma over 2ma squared. And n equals a positive integer. So this is the wave function and the energy eigenvalues for the infinite square well. All right, the delta function. So delta of x is equal to infinity at x equals 0, and otherwise it's equal to 0. It's This is a graphical one. This is the wave function of a finite square well. And you can see between negative a and a, you get a periodic function, and then it damps out beyond minus a. All right. Okay, here's another Hamiltonian to recognize. So this is h equals negative h bar squared over 2m second derivative with respect to x plus b of x, where b of x is equal to 0 between 0 and a, and otherwise is equal to infinity. So this, hopefully you recognize, is the Hamiltonian for an infinite square well as opposed to a finite square well, where b of x is finite. The complex modulus. So this is basically the absolute value squared of a wave function, and it's equal to the complex conjugate of the wave function times the wave function. The position momentum commutator, so x hat and p hat commutation, is equal to I h bar. A Hermitian operator, so for this, the integral from negative infinity to infinity of the complex conjugate of f of x times a hat g of x is equal to the integral from negative infinity to infinity of the complex conjugate of the a hat f of x times g of x. All the eigenvalues are real, and for different eigenvalues, they're all orthogonal eigenfunctions. That's the definition of a Hermitian operator. And we saw this before in bracket notation. This is just the functional notation. Okay. The expectation value of an observable a in integral form. So the expectation value of a is equal to the integral from negative infinity to infinity of the complex conjugate of the wave function times a hat on the wave function dx, as long as a hat is a Hermitian operator. Okay. The general energy time uncertainty guideline. This says that the uncertainty in energy times the uncertainty of time is approximately equal to h bar. It's a guideline. It's not a strict equals there. Wien's displacement law says that the max wavelength is at 2.9 times 10 to the negative third Kelvin meters times temperature to the negative 1, or divided by temperature. So this is the max wavelength for a black body power spectrum. Atom energy states. Negative E sub n equals 1 over n squared E1, where n is 1 or greater positive integer. The Pauli exclusion principle. This says that no two identical fermions can occupy the same quantum state. The de Broglie formula, I don't know how to say that, de Broglie formula, P equals h bar k. Adding spin. So this says that S total equals the absolute value of S minus S prime to S plus S prime in integer steps. And M total is equal to MS plus M prime S. So this is what values are allowed. I'm not sure if I'm explaining that clearly, but so this is the minimum, the absolute value of the difference, and then the maximum is them added, and then it's all the integer steps in between. Those are the allowed values. Okay, the Rydberg formula. So this says that F is proportional to 1 over NF squared minus NI squared. Those are energy states, the N's. Okay, here's another Hamiltonian to recognize. So this is h equals negative h bar squared over 2m, second derivative with respect to x plus b of x, where b of x equals some negative value between negative a and otherwise is 0. And so this is the Hamiltonian for a finite square well, as opposed to an infinite one. The position operator x hat equals x. This might be one of my favorite note cards. I can actually remember that one. Position, momentum, uncertainty. So the uncertainty in x times the uncertainty in p has to be greater than or equal to h bar over 2. The singlet state, this is s equals 0, m equals 0. And it's 1 over the square root of 2 times up, down, minus down, up, bracket, or vectors, eigenvectors, and it's antisymmetric. Singlet state. The Hermitian operator inner product, so if you have A and A hat B, then that also equals A hat A B, right? That's a Hermitian operator. And so that's defined as A Hermitian operator B, because either of those are equal. So the inner product. Normalization of the wave function, so the integral from negative infinity to infinity of the absolute value squared of the wave function over dx is equal to 1. Normalize. Yay. All right, electron orbitals. These are fun. So there's 1s, 2s, 2p, 3s, 3p, 3d, and the number of electrons in those is 22626. Sorry, I messed it up. 2262610. There we go. Position, momentum, commutation relations in 3 dimensions. So the commutation of x and px is equal to I h bar, and that's similarly for y and z. And then the commutation of x and y is 0, and the commutation of x and p of y, or py, is 0. Okay, so if they're not the same, then they're 0. And if they are the same, then it's I h bar. The hydrogen atom ground state energy. Negative E sub 1 is equal to h bar squared over 2 mu a squared. Which is equal to mu e squared squared, e to the 4th, I don't know why I wrote it that way, times 2 times 4 pi epsilon squared times h bar squared. And this is equal to 13.6 electron volts. Diract notation. This is what I've been talking about with the brackets. So on the left, it's a bra, and on the right, it's a ket, and you put them together, it's a bracket. So clever. If you have a bra and a ket, then that means the inner product of A and B, and the inner product of A and B is also equal to the complex conjugate of the inner product of B and A. So you can't just swap them. Wave function incident on a localized potential. So, little psi of x, if x is less than or equal to negative a, is big A e to the I kx plus b, I think I'm missing an e there, e to the minus I kx. And then between negative a and a, it's something, and that depends on what the potential is, right? So like we've been looking at the finite while and the infinite, like stuff like that. So that changes. And then once x is greater than a, then it's big C e to the I kx. So these are the different ways. So for example, for a well, it's sinusoidal. For a barrier, it's an exponential decay between the localized potential. The wave function probability of reflection or transmission. So the probability of reflection is the absolute value of b squared over the absolute value of a squared, and these are the coefficients that we were just on the last one. And the probability of transmission is c squared over a squared, and then the probability of reflection plus transmission is equal to 1. It has to either reflect or transmit. The spectrum of our harmonic oscillator. So Hn is equal to h bar omega times n plus 1/2 times n, where n here is a ket, and the values of n are 0 or a positive integer. the probability of the lambda sub n eigenvalue is equal to the absolute value of c sub n squared, where the wave function of x and t0 is equal to the sum over k of c sub k f sub k of x. So the coefficients, basically, of the wave function terms. Excuse me. All right, here is, again, an equation I wanted to recognize. So it says E sub n is equal to E sub n 0 plus lambda squared, and then the sum over the inner product of h prime with psi sub m and n of 0 squared over en 0 minus em 0. So basically, this is a second order energy shift for perturbations. Okay, the statistical variance measurement. So this says that sigma of a squared is equal to the expectation value of a squared minus the expectation value of a squared. A commutator. So the commutation of a hat and b hat is equal to a hat b hat minus b hat a hat. Adding orbital angular momentum and spin. So then you get J equals L plus S, and the values range between the absolute value of L minus S to L plus S in integer steps. So the minimum, maximum, and then all the integers in between. The harmonic oscillator in 3 dimensions. So little psi sub n of x, y, and z is equal to little psi n1 of x times little psi n2 of y times little psi n3 of z. The energy at n is equal to n plus 3 halves times h bar omega, and n is equal to, the big N is equal to little n1 plus little n2 plus little n3. Okay, the general position momentum uncertainty guidance, so again, this isn't an exact relation, it's a guidance, says that delta x times delta p is approximately h bar. Okay, well, that does it. So thank you so much for watching, and hopefully this was helpful for you, and I wish you the best of luck with your studying and your tests whenever you do take it, and I will see you again soon. All right, bye.